In this lecture, we are going to learn about a very important property in the flow behavior of fluids, which is known as viscosity. So initially, in short, we'll define what viscosity is. So viscosity is internal resistance to motion. So the fluid is offering certain internal resistance to its own motion. It is known as viscosity, and it is denoted by a symbol mu. So details of viscosity we can understand through certain example. But prior to this, we should understand what is the difference between friction and viscosity. How viscosity it is different from friction. Let us consider two solid surfaces. One solid body is stationary and another solid body is moving relative to it. Now what will happen? The stationary solid body surface, it will offer certain resistance to the movement of the second body. And this resistance offered, it is external resistance. Why I am calling it as external resistance? Because resistance, it is at the interface of these two solid bodies. So interface of the two solid bodies, the resistance is going to occur. And it is external because when we consider the whole solid body, the resistance is offered only by the surface of a solid body. It is not offered by entire bulk of the solid body. That's why it is known as external resistance to motion. Whereas when we observe the flow of honey or any thick substance, we can understand that it is not because only of the surface, but it is because of the own fluid resistance. The flow is not that much smoother in case of flow of honey. So this we have understood. Then we'll consider one example through which the viscosity behavior can be understood. So let us consider two systems we have, same size, the same shape of these two funnel shaped systems with spiral bodies we have. And in these two systems, at the same instant, two different fluids are poured. Fluid A poured in this one and fluid B poured in this second one. Now at the same instant when they are getting poured, fluid A, it is getting passed through the system very easily, very smoothly it is getting passed and getting collected in the container. But when we see the second fluid, fluid B, what is happening? The fluid B is not getting passed very smoothly. It is offering more resistance as compared to this one. So we can say that the fluid B is offering more resistance to its motion. That's why it is known as a highly viscous fluid. Whereas fluid A, it is not providing or giving a high resistance to its own motion and it is getting easily moved out. That's why it is known as a low viscous fluid. Now we'll go into the details of viscosity. What exactly this internal resistance to motion it means. So let us consider one flat plate we have over which some fluid is moving. And this flat plate, it is considered to be impermeable. It means that the fluid particles will not get absorbed by this solid surface. Now what we'll consider is, we'll consider that as the fluid particles are coming and when they come in contact with this solid surface, what is going to happen? So this solid surface, though it is appearing to be very smooth, if you see it microscopically, you will observe that the smoothness is not present. The surface is uneven, roughness is there, certain gaps, some unevenness is present in the smooth surface that microscopically you are observing. So what will happen, as the fluid is coming and moving over this body, moving over this plate, the fluid molecules, so they will come in contact with this surface. And now what will happen? There is a chance that the fluid particle or fluid molecule will get clogged in between these spaces. And if it is getting clogged, what will happen? They will come to rest and their velocity will be equal to 0. And hence now we can see here that we have different number of molecules which are coming with certain velocity, but when they come in contact with this uneven surface, they are getting clogged between these gaps and hence coming to rest. Now what will happen? If this plate, it is stationary, the velocity of this fluid particle will be equal to 0. So we can say that at the close contact between this solid surface, whatever the fluid layer we have, the relative velocity of this fluid particles in the layer will be equal to 0. And if the solid plate is stationary, we can say that the velocity of fluid layer in close contact with the solid boundary will be equal to 0. Now this condition, it is known as no slip condition. Why it is known as no slip condition? Because the particles or the molecules, they are getting clogged here and coming to rest. They are not getting slipped away. They are not moving in the forward direction. They have lost their momentum here and coming to rest. That's why it is known as no slip condition. The molecules are not getting slipped away. And then at some section, at one of the section of this plate in y direction, we can consider different number of molecules. Now this molecule which we are considering here, what will happen with this? It will get clogged somewhere in between the gap of this surface, and hence its relative velocity will be equal to 0. As this velocity is equal to 0, what it will do? It will cause disturbance to this upper molecule. So this upper molecule, it will get disturbed because of this, and this is known as what? No slip condition and its consequence. So no slip condition is what? The fluid particle or fluid molecule coming to rest, it is not getting slipped, and its consequence is it is resisting some another molecule which is present in the vertical y direction. So this molecule is getting disturbed by this bottom molecule. So momentum of all the different number of molecules in y direction, they are getting disturbed because of this first molecule which is in close contact with the solid boundary. So this is nothing but known as no slip condition and its consequence. And this is nothing but known as an internal resistance to motion. So here we have fluid, and this resistance provided by molecule 1 to molecule 2, it's an internal resistance provided for its momentum, for its motion. That's why viscosity is known as internal resistance to motion. Now what we'll do is, we'll try to draw a velocity vector for individual molecules. So this molecule, as it is at rest, it will have velocity equal to 0. This molecule velocity, it is shown by this arrow. Definitely the magnitude of this molecule as compared to free stream molecule, it will be less. It is because this momentum of the molecule, it is disturbed or it is reduced because of this stationary molecule, and hence this velocity will be less. Again similarly, we'll draw a velocity vector for this one, for this molecule. As this molecule, it is not in direct contact with this one, the disturbance in the momentum will be less, because of which the reduction in momentum will be less, and you will have some higher velocity. If we join tips of all these velocity vectors by a curve, it will form a parabola, and you can conclude that the velocity distribution is parabolic in nature. Similarly, if we take some another section at the same plate, and again in y direction different number of molecules we are having, and same procedure if we repeat, that is drawing the velocity vectors for each molecule and drawing the profile for it, you will come to know that again it's a velocity distribution you are getting. And now a very important part, that at some in the y direction at some distance, it will happen that the molecule velocity, it will be closely approximately equal to the free stream velocity. So I am saying that this molecule is having velocity 99% as that of the free stream velocity. Again at this section, this molecule may have velocity 99% as that of the free stream velocity. So if I join these points with the help of a locus, it will form certain curve, it will form certain layer, and this layer, it is known as boundary layer. Why it is known as boundary layer? It is because the disturbance in the momentum caused, it is significant only in this portion, but above this portion, above this height, what we have is the disturbance is not that much, because of which we can say that this boundary layer is present, between which or within which we have significant viscosity effects, and above this we don't have that much significant viscosity effects. So this is nothing but no slip condition and its consequence. To understand this, we'll take certain example. Here is one video in which dye particles are inserted here. This is the solid surface, and fluid is moving from this back direction from right to left. Now what is happening here? You can observe at this surface the dye particles are getting adhered. It means that the fluid particles in close contact with the solid boundary, they are having velocity as that of the solid boundary, which is nothing but a no slip condition. And now because of the resistance offered by one molecule to the another, and hence now we can extend this to the surfaces also, layer, fluid surfaces also, fluid layer also. Now If you consider this as one layer, this is the second layer. Because of this disturbance caused by one molecule or one layer to the another layer, there is certain resistance in between these two, resulting in the development of shear stresses between these two, because it's a kind of two layers we have. So one layer, it is resisting the motion of another. So layer is trying to move in the forward direction, but this bottom layer, it is resisting the motion of it. So this is nothing but what? A tangential force acting on an area, which is nothing but force per unit area, that is shear stress. So shear stress will get developed between the two adjacent layers of the fluid. Now, as we understood what is no slip condition and its consequences, and what is the meaning of viscosity and the resistance that is being there in between the two layers, now we should understand what is the origin of this resistance, what is the origin of viscosity. So when we talk about liquids, the origin, it is related with the intermolecular forces of attraction of liquids. Now what this intermolecular force of attraction does, and in case of gases, it is related with transfer of molecular momentum. So we'll go one by one. So if we consider molecular structure of a liquid, if this layer, it is close to the solid boundary, its velocity will be less, and as we move in the y direction, the velocity will continuously go on increasing. That we have seen here. Now what will happen, as there are intermolecular force of attraction present between the molecules, the resistance will be given. This lower velocity molecules, this layer, it will give resistance to this molecules. So they are trying to move in the forward direction, as well as this is trying to move in the forward direction, but because there are some intermolecular force of attraction present in between these layers. So first and second layer, if we consider, this is moving at a lower velocity, and this second layer, it is moving at a higher velocity. So because of this bond, what will happen? These molecules will try to retard its motion, the motion of second layer, whereas the second layer will try to accelerate the motion of first layer. So this retardation and acceleration, it will result in the resistance, which is nothing but viscosity. And in gases, what will happen? So in case of gases, no intermolecular forces we have, but because of that, the origin of resistance, it is not because of intermolecular forces, but it is because of certain another mechanism which is known as transfer of molecular momentum. Now what is the meaning of transfer of molecular momentum? If two layers of gases we are considering, what will happen? The molecules are in random motion. So as there is no intermolecular forces, the molecules can move in anywhere in the random direction. So this random movement of molecules and their vibrations about their center, what it causes? There is a chance that the molecule from this lower velocity layer, it might get entered into the higher velocity layer. Similarly, molecule from the higher velocity layer, it might get entered into the lower velocity layer, and because of which what will happen? If lower velocity molecule entering in higher velocity region, it will try to retard the motion of this higher velocity moving particles. And similarly, when a higher velocity particle, it is getting moved in the lower velocity region, it will try to accelerate this lower layer. And because of this accelerating and retarding action, again there is a development of shear stress between these two, and there is a existence of resistance provided by one layer of a fluid to the another, and this is known as viscosity. So in liquids, intermolecular force of attraction is a significant cause of viscosity, and in gases, transfer of molecular momentum. So this is nothing but a momentum getting transferred from one layer to another. It is a significant momentum we have in case of gases, which results in viscosity.